Bananas, perhaps the cheapest and most common fruit, but also the most fleeting. They are known for going from perfect to overripe in seemingly seconds. Enter the beauty of banana bread, which has the ability to turn this fruit past its prime into something wonderful. Banana bread represents a sort of resourcefulness, perhaps indicative of the time in which it gained popularity back in the 1930s, and the baking of which has remained a source of comfort and deliciousness since. With such a strong appreciation for the baked good, we wanted to better understand how to bake the best loaf of banana bread possible, which requires a dive into the realm of heat transport.
Let's start by looking at an oven. Conventional ovens use heating elements to heat the air inside the oven to cook food, while convection ovens have an additional fan to circulate air. But why would this make a difference in cooking? The answer? Convection, a method of heat transfer through a fluid. Conventional ovens use natural convection, which occurs because of natural airflow within a space. In contrast, convection ovens create a velocity to move the air, and this is called forced convection. Newton's law of cooling shows us one way to understand convection, showing Q, heat flow, as a function of the heat transfer coefficient, area, and the change in temperature. In an oven, heat travels from the heating elements to the air, and then to the banana bread. But that's not all. There's another type of heat transfer occurring here, conduction. Fourier's law of conduction demonstrates this with the heat flow Q, once again, but this time it's a function of the thermal conductivity of a material like the baking pan, the area, once again, and the gradient of temperature. So ovens use two methods of heat transfer, convection and conduction.
Now we'll be learning a little bit about radiation in microwaves. Inside the metal box shown here, known as a microwave, there is a microwave generator called a magnetron. When you start cooking, the magnetron takes electricity from the power outlet and converts it into high-powered microwaves. The magnetron then blasts these waves into the compartment of the microwave holding the food through a channel called a waveguide. The food sits on a turntable and starts spinning slowly so that the microwaves cook the food evenly. The microwaves also bounce back and forth of the reflective metal walls of the food compartment so that they're not lost. Lastly, as the food absorbs the waves, the molecules begin to move faster and vibrate. These vibrations of the food molecules cause the food itself to heat up rapidly. Thus, the microwaves pass their energy into the molecules in the food, which causes the food to rapidly heat up. Microwaves utilize electromagnetic waves that are emitted in the microwave region of the spectrum. These microwaves are unique in that they're well absorbed by water, fats, and sugars, which is most abundant in our daily foods. Once they're absorbed by these molecules, they are directly converted to heat as the molecules increase in random motion. Uniquely, microwaves are not absorbed by most plastic, glass, or ceramics, which are often used to hold our daily foods. This optimizes the heating of the food since all the waves will be absorbed only by the food and will not be lost to anything else present in this microwave. Radiation is energy that is emitted in the form of photons or electromagnetic waves and is the type of heat transfer that is utilized in microwaves. Specifically in microwaves, as the electromagnetic waves are emitted, the food particles begin to move faster and gain heat. Thermal transport by radiation in this microwave follows the Stefan-Boltzmann law. Here, Q is the rate of heat being transferred, A is the surface area of the object, T1 is the temperature of the source, while T2 is the temperature of the object being heated. HR can be broken down further, where Tm is the mean temperature between the source and object. The epsilon is the emissivity, or the ratio emitted by the source in comparison to a perfect emitter, such as a black body. Sigma is the Stefan-Boltzmann law constant, and F is the view factor, or the fraction of energy that is emitted by the source and seen by the object.
In order to determine the best method of baking banana bread, we decided to investigate the differences in baking speed and baking quality between the different types of bakeware and the different types of heat transfer. We chose to compare the banana bread made in two different bakeware materials, ceramic and glass. Additionally, we would compare the two different types of heat transfer, radiation in the microwave versus conduction and convection in the oven. To perform our experiment, we made 4 batches of banana bread. We first cooked the banana bread in the ceramic mug in the microwave, until it appeared to be fully cooked and surpassed an internal temperature of 93 degrees Celsius. Every 20 seconds of cook time, we removed the mug from the microwave to check the internal temperature with the food thermometer and recorded the data. We then repeated this procedure with the glass mug in the microwave. Next, we cooked the banana bread in the oven in the ceramic mug, checking and recording the temperature every 3 minutes until the bread was fully cooked. Finally, we baked the last round of bread in the glass mug in the oven and recorded the data. Here are the quantitative results of the temperature data points plotted against time for the microwave and the oven. The blue lines represent the data for the ceramic mugs, and the orange lines represent the data for the glass mugs. The microwave took 3 minutes to cook the banana bread, regardless of the mug material. There was very little variation in the temperatures between each mug, and both mugs ended the 3 minutes at 102.2 degrees Celsius. The oven took 36 minutes to cook the banana breads, and once again both mugs were cooked in the same amount of time. The ceramic mug ended at 96.5 degrees Celsius, and the glass mug ended at 96.1 degrees Celsius. The similarities in temperatures between each mug type can likely be attributed to the fact that ceramic and glass have very similar heat transfer properties. Our qualitative results were concluded by comparing the cross-sections of the banana breads cooked in both types of mugs with both types of heat transfer. Seen on the left are the breads cooked in the microwave, and seen on the right are the breads cooked in the oven. The top row of banana bread comes from the ceramic mug, and the bottom row comes from the glass mug. As you can see, there is essentially no difference between the appearance of the bread based on the type of mug. The biggest and most obvious difference comes from the comparison of the textures in the microwave bread versus the oven bread. The microwave bread is the most well done in the center, with the edges being paler and more underdone. On the other hand, the oven-baked bread was the most well done on the outside, with a lighter center. This phenomena can be explained by considering the methods of baking in each appliance. The microwave radiation only heats up water molecules, therefore the mug is not heated directly, and the bread is cooked from the inside out. In the oven, the hot air surrounding the banana bread heats up both the mug and the batter, therefore cooking the bread from the outside in as the heat transfers through the materials. Finally, we want to consider how this experiment could be improved in order to produce higher quality data and conclusions. First, we could invest in a better food thermometer with a faster temperature reading. The thermometer used in this experiment's temperature readings fluctuated greatly, and we often had to wait up to 30 seconds for the reading to stabilize. A faster thermometer would allow for more accurate readings while eliminating the heat loss when waiting for the reading to stabilize. Next, we could compare bakeware materials with a greater difference in heat transfer properties. Ceramic and glass are very similar materials, so comparing more dissimilar materials could provide more compelling results. Examples could include metal or silicone bakeware. Finally, we could try other methods of baking with less potential for error. We can assume that a significant amount of heat was lost from the banana bread batter when it was removed from the microwave or oven to take the temperature. An example of a better designed procedure would be cooking the mugs in an open pot with boiling water and taking the temperature from above, therefore eliminating the need to remove the bread from the heat source for data collection.
Overall, using a microwave to make banana bread is much more efficient, but the quality is much higher when baked in the oven. Additionally, we didn't notice much of a difference between a glass or ceramic baking vessel. However, we encourage you to go out and conduct your own experiments, if not to explore the concepts of heat transfer, then to at least enjoy a delicious slice of banana bread. Thank you.